All right, starting the last lesson of the year, 9.7b probability. All right, two events are mutually exclusive if they have no events in common. Okay, here's some new notation coming up here. All right, intersection is an upside down U, union is an upright U. All right, so here we have the probability of the intersection of events A and B is equal to 0. So mutually exclusive means they don't share any outcomes together. So let me go below here, and this may clarify the idea. The probability of the union of two events. If A and B are mutually exclusive, meaning they don't share any events in common, then the probability of combining them both together is simply the sum of their probabilities. Now, if the events are not mutually exclusive, okay, then the probability of the union of the two events is the sum of the probabilities of each minus the probability of the intersection of the events. All right, now here's a little visual on the right side to help solidify the understanding of this idea. All right, so if you have the union of two events and they're mutually exclusive, all right, mutually exclusive means they don't overlap at all. Okay, so if I want to find out the probability of that, I simply take the probability of each event. Now for the next one, if they're not mutually exclusive, then I take the probability of each event. All right, but when I did that, look at this piece right here. I essentially counted that area twice, and you don't want to count it twice. So I'm going to subtract that intersection once. All right, and that will give me the actual probability. All right, now for example one card is selected from a standard deck of 52 playing cards. What is the probability that the card is either a club or an ace? Okay, so club or an ace. Are these events mutually exclusive? They are not mutually exclusive. All right. All right, that means that there's an overlap. You could have a card that's both a club and an ace. Okay, so these two events are not mutually exclusive. All right, so we'll say the probability of event A is having a club, and event B represents an ace. So what's the probability of getting both a club and an ace? In other words, the union of those two events. Well, it's going to be the probability of A plus the probability of B. But since they're not mutually exclusive, that means there's an overlap. And I have to subtract that overlap. All right, they intersect. All right, so what's the probability of getting a club? Well, how many clubs are there in a deck of cards? There's 13 out of 52. What's the probability of getting an ace? Well, there's 4 aces in a deck of cards, 4 out of 52. And what's the overlap? How many cards are there that are both a club and an ace? There's 1. Alrighty. So working this out and simplifying, we get 5 over 26. Done. All right, for the next example, at the end of 1998, there were approximately 117 million wage and salary workers employed in the United States. The circle graph gives the age profile of these workers. Okay, what is the probability that a person selected at random from the population of wage and salary workers is in the 35 to 44 age group? 35 to 44? Okay, that's pretty straightforward. Not much thinking involved there. For part B, what is the probability that a person selected at random from the population of wage and salary workers is in the 35 to 54 age group? 35 to 44 and then 45 to 54, so it's these two combined. All right, so 27 plus 20, 47%. That was super easy. Not much thinking involved there. All right, next idea. Two events are independent if the occurrence of one does not affect the occurrence of the other. All right, the probability of independent events. So what's the probability of event A and B? All right, if they're independent events, it's the probability of A times the probability of B. So let's go through a couple examples of this. Two integers from 1 to 30 are chosen by a random number generator. What is the probability that both numbers are less than 12? All right, well, how many numbers are there less than 12? There's 11, 1 through 11. So there's 11 numbers, and out of how many to choose from? 30. All right, well, when I'm choosing the next number, does what took place before have any effect on what's taking place now? No. That means they're independent events. So you're going to be multiplying these probabilities. So it's 121 over 900. Done. All right, example 4. A sales rep makes a sale at approximately 1/3 of all calls. If on a given day the representative contacts 5 potential clients, what is the probability that a sale will be made with each of the 5 contacts? All right, he contacts one client. What's the probability that he makes a sale? 1/3. Then he calls up the next client. What's the probability that he makes a sale? Well, does what took place with the previous call have any impact on this current call? No, they're independent events. So it's 1/3 again, and we're multiplying, and the same idea continues to apply. All right, we multiply all these, we get 1 over 243. Done. All right, next concept, the complement. The complement of an event is a collection of all the outcomes that are not in the event. The complement event is denoted as A apostrophe, or in other words, A prime. Call this A prime. All right. And we have the probability of a complement here. So the probability of a complement is 1 minus the probability of the original event. Now, why do they use 1? Well, here's a key question. What do all the probabilities in a set add up to? They all add up to 1, always. Okay? So if I have an event and I want to know the probability of all the events outside that event, then I'll just take what they all add up to, and I'll just subtract the probability of that event. Okay? And it works the other way as well. So if I want to know the probability of all of these events here, well, the whole thing, all the probabilities add up to 1. So if I want to know the probabilities of all of these, okay, I'll just subtract the probability of A, and that would equal the probability of the complement. All right, very basic idea. All right, example 5. And this idea is actually very powerful when working with probability problems. You'll see in this example here. A sales representative makes a sale at approximately 1/3 of all calls. If on a given day the representative contacts 5 potential clients, what is the probability that a sale will be made with at least one contact? So the probability of at least one contact. All right. Well, probability of at least one contact means I have to figure out the probability of 1 contact plus the probability of 2 contacts plus the probability of 3 contacts plus the probability of 4 contacts plus the probability of 5. All right, you have to figure out all those. But here's the power of the complement idea. Okay, well, what's the complement of at least 1? What's the other probability that's not included? The probability of 0, right? The probability of no sales. 0 sales. All right, and what am I going to subtract that from? Well, what do all of the probabilities add up to? 1. So I just subtract that from 1, and boom, I got my probability. That saves you a lot of time. So I have 1 minus, what's the probability of no sales? Well, it's going to be 2/3 times 2/3 times 2/3 times 2/3 times 2/3. Because if there's a 1/3 probability that you make the sale, then there's a 2/3 probability that you don't make the sale. And you're calling up 5 people. All right, so I have 1 minus 32 over 243. Oops, 243. And so I end up with 211 over 243. That is all there is to it. Done. All right, if you have any questions, please make sure to ask. Begin the assignment at the bottom of the page.